Good afternoon, everyone. Hope you guys enjoyed the eclipse. How many of you guys went to the Path of Totality? Most of you? Yeah, I think it was well worth it. All right, so we're going to start a new unit today, something called Principal Component Analysis. I'm curious how many people have heard of PCA? Okay, a few of you guys. So PCA is a little bit, let's see. I'm going to see if I can change something. Okay. All right, so PCA is sort of a different task than we have, or what we're doing with PCA is a very different task than we have considered until now. So the idea is that it's common that when you have a data set, the feature dimension D can be quite large, and there's many motivations for reducing the feature dimension if possible. Maybe you want to simplify the computation of classification or regression. Maybe you want to save memory or storage. Maybe you want to help visualize the features, because if you have high dimensional features, it's difficult to draw them, but if you can reduce them to 2 dimensions, you can plot them very, very easily. So there's all these motivations to reduce the dimensionality, and PCA is the most classical, well-known approach to do that. It is, in particular, it is RSS optimal and linear, and those two things together make it possible for us to analyze it and derive it in closed form, similar to how we did linear regression. That was linear, that was RSS. As you know, once we try to do more complicated things, then they become less tractable. It's much more difficult to derive the solutions and so on. So PCA is not a cutting edge approach. It is a very classical approach. I think it was proposed around 1901, so super old, but it shows up everywhere. So that's our motivation to learn about it. If you're interested in visualizing data, taking high dimensional data and reducing it to 2 dimensions or so to visualize it, cutting edge techniques include t-SNE and UMAP, and we'll briefly talk about those later, just for completeness. All right, so in this unit, our data set is going to consist of only feature vectors. So in other words, there's not going to be any targets or labels in the data. Okay, so all we have are these X vectors. As usual, we're going to have n of them. And as usual, the dimension of them is going to be D. So there's going to be, in every feature vector, there's going to be D scalar entries. And as we've always done, we can store those features as the rows in a matrix, capital X, and that will represent our entire data set. In this unit, just to keep the notation simple, we're going to assume the data is centered, meaning the mean has been removed. The sample mean has been removed so that when you sum all the features or average all the feature vectors together, you get 0. It's not essential for the methodology. It's just it makes the notation simpler. And obviously, that's a very simple thing to do. If you're given a data set, you can just easily compute and subtract the mean. Okay, so again, in this application, for the first time in the course, we're considering some sort of machine learning without targets or labels. This is known as unsupervised learning. That contrasts with supervised learning, which we've considered until now, for which we've thought about classification and regression. So unsupervised learning is what we're going to spend the rest of the term on. And here we have dimensionality reduction, and then in the next unit, we'll consider clustering as another task of unsupervised learning. And so the main question we're asking in this unit is, can we compress the features down from D to some much smaller number without losing much information? So that's our goal. Okay. Any questions so far? Okay, so so as we'll see, today is going to be a lot of linear algebra, but let's just get started. So there's basically two main ideas in PCA. The first idea is linear approximation. And in this linear approximation idea, essentially what we're going to try to do is we're going to try to construct an approximation of the ith feature vector, which is a fixed matrix B that we design that is going to be in common for all I. And that's going to be a tall matrix. So we have a picture like this, a vector is approximately equal to a tall matrix B times a short vector Zi. So that's what we have here. So essentially we're going to be representing xi with this short vector Zi, and that short vector is going to contain capital R elements. Ideally, we want capital R to be much less than D, so that we're representing xi with a vector that is a lot shorter, a lot fewer coefficients. So we're going to, for every xi, we want to design B and Zi. We can think of B as consisting of a dictionary of different elements, and these Zi's are some coefficients that we use to linearly combine the dictionary coefficients to make xi. So the question then is, how do I form the best dictionary to represent my entire data set so that with those few capital R dictionary elements, they can be linearly combined to get close to any vector in the data set. That's the objective. So B is a dictionary, Z is combining coefficients. And a key point is that this construction or this approximation is linear. So there's certainly much more sophisticated ways of doing this. Examples of this that you've heard of would be like JPEG, MPEG, for like if xi was an image, you could use JPEG compression. If xi was an audio file, you could use MPEG or MP3 or whatever. So those techniques are much more sophisticated. They can do compression much better, but they're much more complicated, and they can't really be, we can't just write down equations and do linear algebra and find the solution. If we take this simple linear approach, and second, if we consider our goal is minimizing RSS, then we can do the analysis and we can learn some fundamental ideas, or we can involve some fundamental ideas from linear algebra. And that's really the spirit of PCA, is just sort of understanding some particular math and how it applies to compression and representing data. Okay, so here on the top we have this linear approximation, and on the bottom we have our design objective, which is to find the B matrix and all the Zi vectors to minimize the RSS between the original data and our approximation. Yeah, and this is principal components analysis. This is what PCA is. So the use of the linearity, we said, is not optimal. It's just done for simplicity. The same is true of RSS. It is maybe not the right thing for all tasks. For example, if we're really interested in classification where perhaps we do have some labels yi, and we want to compress our features down to some smaller, shorter vectors Zi, so that we can maybe represent our data or train a classifier quicker or something. Then, if we use RSS to do this compression, we could actually have some really bad results. We don't expect PCA to improve our classification performance. it's really just a compression technique which could have advantages in terms of storage, computation, things like that, but we wouldn't expect the performance to increase. We'll talk specifically about why that is. In particular, when you use RSS, that can be a really bad match to classification. We'll talk about that a little bit later. But again, RSS is chosen for simplicity, really nothing else. I guess there are a lot of applications where RSS would be the right goal, but it's not correct in general.
In this case, is R like a design parameter?
Yes, R is a design parameter, and we'll talk specifically about how we can choose it. We'll construct a metric similar to R squared that we use in linear regression, which will be very similar, but it'll be for PCA, and we'll see like how the choice of R affects that parameter. We'll do some experiments. Okay, so that's sort of the two main ideas behind PCA: linear, RSS, and compressing the feature vector xi to a much shorter vector zi. Okay, any questions so far? Okay, great. So first I'll tell you what the solution is, just as kind of a sneak preview, and then we will derive it later. So the solution for B, this matrix, we'll call B hat the RSS minimizing B. The way you construct it is first you look at the sample covariance matrix of the data. We're not subtracting the mean here because we already assume that the mean has been subtracted. Usually you would see the mean subtracted here, but we don't need to do that. And so from this data set, we can get the sample covariance matrix Q. And then you do an eigenvalue decomposition of this matrix. You look at the largest eigenvalues, in particular the R largest eigenvalues, and then you look at the corresponding eigenvectors that match those eigenvalues. You take those, what are called now the principal eigenvectors of that sample covariance matrix. You stack them together like this as columns in this matrix. We'll call it V sub R, and that is the optimal dictionary. Second, the optimal approximation coefficients, we'll call those Z hat I. That is going to be the original feature vector multiplied on the left by VR transpose. So it's really all about getting this VR matrix, and then that's sort of the key idea for PCA. These principal eigenvectors here, these are also called the principal components. That's where the name comes from. Okay, so just as a visual example, imagine we have data in 3 dimensions. So here on the left, you can see we have 1, 2, 3 dimensions. These circles, you can ignore the color of the circles, just these are little points in 3 dimensions. If you compute the covariance matrix of this data and you look at those 2 principal eigenvectors, you will find that they point in directions for which their linear combinations form this plane. And that plane is the plane of greatest variation, of the 2-dimensional plane with greatest variation for that data set. If you do, that's a 2-dimensional approximation. If you instead do a 1-dimensional approximation, then you take the single, the principal eigenvector, the one that corresponds to the largest eigenvalue in your autocovariance matrix, your covariance matrix. That goes along this dimension, and that is the single direction of greatest variation in your data set. So of all those dots here, they are, the greatest variation is along that direction. And what PCA actually does is it projects onto the subspace spanned by those principal components. So the principal components are the two vectors that define this plane. And then what PCA does in making the approximation is it projects all of the original data points onto the plane. And now those projections, those are the PCA approximations. So it's basically saying, like, of all the planes I can possibly construct of dimension 2, which plane, what is the plane such that my data is essentially closest to that plane? My data points are closer to that plane in Euclidean distance, squared Euclidean distance. This would be a plane, and then you could also ask the question, along what line could I construct such that all the points in my original data are closest to that line in squared Euclidean distance. Once you know that line, you say, okay, I will project my points onto that line, and now those points, that is my approximation. So we'll see another interpretation in a moment, but that is one way we can think about it. Okay, so the question that we'll try to answer today is why? Why is this the correct solution? Can we derive it just from first principles? So that's what we'll do. And we'll get a lot of intuition about projection and other things as well. Okay, any questions so far? Okay. So to derive it, we're going to basically take two steps. The first step we'll see is really easy. Optimize the coefficients Zi for an arbitrary choice of the dictionary B. Second, optimize that dictionary B. So the first step is essentially just one line. If you fix B, and so this is, again, what we're doing is this. So we're saying, okay, for the moment, just accept an arbitrary B and do this optimization over Zi. So for that problem, we just have this. And this is a problem that we have seen before back in Unit 2. We had slightly different names. We had A and beta, but otherwise it was identical. Oh, and I guess we had Y. Otherwise, it was identical. And so what we found there is we derive from first principles that this was the solution. This is the least squares solution for the Zi's, or it used to be for the betas, and we had that equation previously. Now we just have the same equation, we just change the notation up, and this is what we get for the first step. So if we knew what B was, then this would be the solution for Z hat I. The hard thing is figuring out what B is. So that's what we do next. Okay, so highlight this. Okay, so let's say we're going to use this solution for Z hat I, for Zi. So we can plug that back into this equation here. And now we have an optimization that's only over B. So this is our Z hat I from above, or B times Zi from above is this. And so now we have an optimization problem just in B. But as you can see, it's kind of complicated because we have B appearing 4 times. A couple of them are inside this inverse. So yeah, how do we solve this problem? Okay, so as a very first step, rather than writing xi in 2 places, let's realize that this is I times xi. So we can have xi in one place. We have identity here. And now we can have this one big matrix that we can call PB perp. Essentially, I don't know how many of you guys have seen things like this, but this, if you've seen it before, you might recognize that this is what's called a projection matrix, and this I minus this is also a projection matrix. So, in particular, an orthogonal projection matrix. So, what is this orthogonal projection idea? Okay, so first, let's just review some linear algebra. So, what do we mean when we talk about a subspace? So, in linear algebra, a subspace is a set of vectors that has one important property. Every vector in that set, for any vector in that set, you must also have in that set all scaled copies of that vector. So essentially, examples of subspaces would be a plane, but that plane must go through the origin. Or a line, but again, that line must go through the origin. So those are examples of subspaces. So a particular way to make a subspace is what's from a matrix is known as the column space of that matrix. And the column space of a matrix is basically just the set of all linear combinations of those columns of B. So in other words, we're saying the set of all vectors B times Z, where Z can be any vector. So here Z is just combining, linearly scaling and combining the columns of B, and Z can be anything. So that gives you this big set of vectors, which, for example, could give you this entire plane. Of course, the plane goes infinitely in every direction, but this is just how we draw it. Okay, so that's what the column space of B is. And one thing we might do is consider projecting a vector onto that column space. So here's the picture. So let's say X is this vector. In this picture here, just to make it, to be able to draw it, we're essentially choosing X as a three-dimensional vector. It lives in some three-dimensional space, but the math holds for any dimension. So here, X is in a three-dimensional space. The matrix B in this picture would have two columns. And so when you consider all linear combinations of those two columns, that sketches out this plane. And so now we're talking about what is the projection of X onto that plane. So essentially, that's just the closest vector to X in the plane. So if X is here, this is the origin here. If X is here, one way you can imagine finding the closest vector to this, and this is close in Euclidean distance. Imagine creating a ball of points with some radius around that point. And then you gradually expand that ball, expand it, until it just barely touches the plane. It just touches it at one point. So everything along the surface of that ball is an equal distance away from X, right? But there's only one point in the ball that is in the column space here. That is going to be the closest point to that column space. Right? And if you think about it, the direct path from the center to that edge point of the ball, that is going to that's going to be perpendicular to this plane. So in other words, you can write X as the projection, X hat we'll call it, into the plane plus an error, we'll call it E, that is orthogonal to the plane. That's how it always turns out. And it turns out that you can compute this X hat using a matrix multiplication. You can multiply X by a particular matrix, and it will return this projection. That matrix turns out to be this. This is the matrix that takes you from X to this projection X hat. You can also compute this E vector if we relocate E over here so that it's starting at the origin. You can also compute E from X, and you do that using this matrix PB perp. And that's just I minus PB. I guess that makes sense because together x and x hat and e give you x. So these two matrices have to add up to identity. So that's just sort of a review. I'm sure you guys have seen this sometime in a linear algebra course, or maybe other courses too. That's what orthogonal projection is. Okay, and these matrices, PB and PB perp, have two particular properties. Two and only two properties are needed to construct one of these orthogonal projection matrices. Number one, they must be symmetric. And number two, they must be idempotent. Okay, so symmetry is easy. It's just P equals its transpose. What it means to be idempotent is that if you square the PB matrix, now that's not squaring each term in it, that's PB times PB itself, squaring it that way, that must equal PB itself. So squaring it does nothing. The intuition is that if you take a point and you project it into the plane, and then you project again this new point into the plane, nothing happens in that second projection because it's already in the plane. So doing PB once and then again is the same thing as doing PB once. So that's how we can interpret that idempotency. Okay. One other property is that if you look at the eigenvalues of PB, we'll talk about eigenvalues later, you'll find that PB has exactly R eigenvalues that equal 1, and all of its other eigenvalues equal to 0, whereas PB perp is the opposite. It has R eigenvalues equal to 0, and all other eigenvalues are equal to 1. Okay. These are just little things we'll use along the way. Okay, so this is orthogonal projection, and here, this is one of these projection matrices. So using these ideas, we can now have a more clear understanding of what PCA is doing. Any questions before we move on? Okay, so keep in mind that this is what PCA is minimizing here. Here's writing the same problem again. So this is looking at, this thing is like, you could say EI. It's like you project the point xi onto the column space of B, and then this is the error in the projection error. So for example, I take a point, I project it onto this column space. This thing is defined by, this is basically, this way. This is column space of B. And the vector that takes me from here to here, that is this error vector. If I consider this point, the error vector is that. If I consider this point, the error vector is that. So what this is saying is that the sum squared of the norm of the error vectors should be minimized. In other words, PCA tries to manipulate the B matrix, which therefore manipulates where this plane is located, until this sum squared projection error is minimized for all the points in the data set. And so as you move B around, you move that plane around. If I move the plane, over here, I'm going to have massive errors. That's not going to be the good solution. I try to just position it so that it's essentially closest on average to the data, closest in the squared Euclidean sense. So that's essentially what PCA is doing. Does that help to visualize it? All right. How is this different from some of the pictures we saw back in Unit 2? We actually had similar errors and regression planes. Does anybody remember how they were different?
In Unit 2, you were trying to get things to be farther away from the plane, or not split up.
No, we were minimizing RSS, and so we were trying to get we were trying to move the plane so it again was closest to the points in terms of minimizing RSS. But RSS actually looked a little bit different. Does anybody remember? How is RSS different?
RSS is
Vertical, exactly. So back in Unit 2, this was YI, and so we were all of these projections were vertically down because we were measuring the distance between like YI and Y hat I. So that's now different. We don't have any Ys. So instead of measuring vertical distances in that Y domain, we're actually just measuring these perpendicular distances in the original feature domain. So that's the difference between Unit 2 and what we're doing now. Okay, good. Any questions so far? Okay. All right, so PCA chooses B to minimize the sum squared projection error. That's essentially what it's doing. Okay, so now that we have some intuition, we have to get back to the math to figure out, okay, how exactly do you do this optimization? So we're just going to kind of do a whole bunch of linear algebra now, step by step. So this is where we start. Let's define this cost. This is our cost. B is our parameters. We're trying to manipulate our parameters to minimize our cost. Our cost has a vector inside a squared norm. So for example, if we had like A squared, we know we can write that as A transpose A. So by doing that, we get this times this. And now we can simplify what's in the middle here because remember that being a projection matrix, this guy is symmetric, so we can just imagine we remove the transpose, nothing changes. Second, it's idempotent, so PB squared, PB perp squared, is the same thing as PB perp once. So essentially we can simplify it down to this. Okay, so that's the beginning. Next, this is a scalar, right? This is like row vector, matrix, column vector. So this is a scalar. So as you know, what the trace is the sum of the diagonal elements of a matrix. A scalar is an example of a matrix. It's a one-by-one matrix. But the trace of a scalar and the trace and the scalar without the trace, that's the same because I have one diagonal term. So essentially what I could do is I could put a trace around this term without changing anything. The reason we use the trace often is because it has this really cool property where if you have the trace of a product of two matrices, you can swap the order of the matrices. That is something you usually cannot do in linear algebra. You can't commute. But when these matrices are inside a trace, you can commute. So that's the trick we can use. And now we can think of this xi transpose as the first matrix, PB perp xi is the second matrix. We can swap them, and we get this. Okay. Now the trace is also linear, so I can move the sum inside the trace. Matrix multiplication is linear, so I can move the sum through the PB perp over here. And the last thing I can do is I can put a 1 over n in front of the sum to make it an average, as long as I compensate by putting an n outside here. And the reason we're doing this is now we can see that this quantity is our sample covariance matrix because we already removed the mean. So now we just don't have to write the sum of the xi's anymore. We can just think about that as q. That's something we can compute and just call q. Okay, so that brings us to essentially this problem. So we boiled the problem down to here. And it turns out there's this theorem from back in 1936, the Eckert-Young theorem, that says, okay, if you're minimizing B in this way, what you do is you look at the eigenvectors of Q, as we mentioned before. In fact, you look at the R eigenvectors that correspond to the R largest eigenvalues, stack them in a matrix, call that V sub R, and that is the solution, the B that minimizes this. Okay, so a little bit of background here. What are eigenvectors and eigenvalues if you don't remember? So the first thing is, okay, we talked about computing eigenvectors of Q. Well, can you even do this? Because not all matrices have eigenvectors. And the form of the eigen decomposition is it's different for different matrices. So first of all, if I have a non-squared matrix, there's no such thing as eigenvectors, eigenvalues. So fortunately, Q is square. So that means that, yes, we can compute eigenvectors and eigenvalues. But in general, these eigenvalues could be complex valued. Turns out in this case, they're not complex valued. That is because there's a very special thing about Q, which is known as a positive semi-definite matrix. So when Q is positive semi-definite, or all positive semi-definite matrices have a special eigendecomposition, the simplest one you can imagine. It looks like this. It means you can write the matrix as a matrix V that is orthogonal times a diagonal matrix lambda times that same matrix V transpose. Okay, what does an orthogonal matrix mean? An orthogonal matrix is a square matrix where all the columns are orthogonal to each other and they're all unit norm. It turns out that when those things hold true, then all the rows are also orthogonal to each other and all the rows are also unit norm. So putting those two things together, you can, for example, write V times V transpose. That will give you the identity. This is just a d-dimensional identity. Or you can write V transpose times V. That will also give you the same identity. Okay, so these are nice properties of orthogonal matrices that sometimes allow us just, when we see this, we immediately know, oh, that's just identity. It vanishes. Second of all, in this, okay, so the columns of this V matrix, those are our eigenvectors. And the terms along this diagonal matrix lambda, these lowercase lambdas here, those are our eigenvalues. And it turns out for these positive semi-definite matrices, all the eigenvalues are not only real, but they're actually non-negative. Okay, so that's very convenient, simplifies our life greatly. And the last question is, well, what is this whole positive semi-definite thing? So all that's saying is that if you surround Q by X transpose on the left and the same X on the right, that reduces it to a scalar, that scalar is guaranteed to be non-negative no matter what X is. So it turns out we can easily convince ourselves that this is going to be the case for our Q, because our Q is a sample covariance matrix. So how does this go? All right, here's the proof. You start with this. You plug in the construction of Q. We constructed it this way. Due to linearity, I can move the X transpose in here. I can, these parentheses are there just for clarity. They're not really doing much else. So I can also write the parentheses this way for clarity. So here I have X transpose times Xi, and on the left I have Xi transpose times X, like this. Both of these guys are scalars. And in fact, they're the same scalar, because if I transpose this, I get this. But transposing a scalar does nothing to it. So there's just two different ways of writing the same thing. So in other words, I can just write that times itself as that thing squared. And finally, when you look at this, you see, okay, these terms are obviously non-negative individually. And I'm looking at the average of non-negative terms. So that also has to be non-negative. So that's the end of the proof. Okay, so to recap, anytime you have a sample covariance matrix, you know it's positive semi-definite. And that means when you look at its eigendecomposition, you have this nice property that the eigenvector matrix is orthogonal. The eigenvalues are real and non-negative. Okay, so just a bunch of background. You probably, again, saw this in a linear algebra class at some point, but just to jog your memory. Without loss of generality, just for our notational simplicity, we're going to assume that these eigenvalues have been sorted from large to small. That's generally not the case when you run an eigenvalue solver. It does not sort them for you, so you have to be careful when you do this in practice. They may not be sorted, but we'll just assume that we've also sorted them. So lambda 1 is going to be the largest eigenvalue, lambda d is the smallest. It could be that some are tied, but they'll just be non-increasing after sorting. Okay, so this was the Eckert-Young theorem. This is the thing we're now going to try to prove. Why is the minimization of this given by these principal R eigenvectors? Okay, so technicality is actually, the solution is a little bit more general. This is one way to construct it. Now, actually, any B matrix for which the column space of B matches the column space of these eigenvectors will also work. For example, I can shuffle these different columns around. That is also going to work fine for B, because at the end of the day, I just really am going to use the column space of B, and shuffling these doesn't change the column space. In fact, I can take this matrix and I can multiply on the right by any R-dimensional orthogonal matrix, and that won't change the column space either, and so that will also work for PCA. But we're just going to try to prove that this is at least one of the solutions. Okay, any questions so far? All right, so let's dive into the proof. So this is the cost that we currently have. This is the thing we want to minimize over B. We can remember that this PB perp, this is the orthogonal projection matrix. This is just I minus PB. So we'll put that in there. Now this can carry out this multiplication. This is going to be I times Q is Q, Q minus PB. Because the trace is linear, that's going to be N trace Q minus N trace PBQ. And if I want to minimize this whole thing, you can see that this first part doesn't really matter. So I just want to minimize this right term. And because of the negative sign, I could equivalently just maximize this trace. So we're going to come up with, we're just going to call this U. Instead of a cost, it's a utility. Now our objective is to maximize that thing. Okay, so to do that, we'll take Q, plug in its eigenvalue decomposition, and now we can use this nice trace property, and we can move this part to the front, and so we get V transpose PB V lambda. And this has an interesting structure. If you think about it, there's some matrix. The first part times this diagonal matrix. And what we're doing is we're looking at the trace of this product. So we're looking at the sum of the diagonal terms of this product. Well, because the second matrix lambda is diagonal, when I look at the diagonal terms of the product, I'm going to get the diagonal term of this matrix times that diagonal term. That's going to be the first top left diagonal term of this. Then the next diagonal term of this matrix times the next diagonal term of this, and so on. So essentially, this trace is going to have this form. So over here, the diagonal terms of lambda are these lambda j's, and the diagonal terms of this matrix we're going to call alpha j, the jth diagonal term. Okay, so here it is. Alpha sub j is you take this matrix and you look at the jth diagonal term. Okay, so is it clear why this reduces to this? Okay, and then next, remember that the way we constructed V, this big matrix V, is that the jth column of V was just little vj, the jth eigenvector. And so when I look at the jth diagonal term, that's just vj transpose on the left times pb times vj on the right. Okay, so that's what alpha j is. Now, alpha j has a couple important properties. So first of all, let's convince ourselves that alpha j is always between 0 and 1. So to do that, we'll start with this expression for it. But remember that because this PB is a projection matrix, we can actually replace it with PB transpose times PB. because of the idempotency and the transpose property. This is kind of going backwards from what we did before. And now that we have this, we can see that this is just the norm of this vector squared. And because this PB, when you project, you either keep the matrix or you shrink it. The squared norm of PBV is upper bounded by the squared norm of VJ itself. And these guys, as we said, they're columns of an orthogonal matrix, so they're all unit norm. So this is just 1. So above, the alpha j is bounded by 1. And from below, you can see that this can never be negative, so the smallest value it could be would be 0. Okay, so alpha j is going to be between 0 and 1. Second, let's look at the sum of the alpha j's across all the different j's from 1 to d. So for that, the sum of the alpha j's is actually just the trace of this first part here. And we can play our trace trick again. We can move v to the left side. And now I have v times v transpose, which we know is identity. So that goes away. We just have the trace of PB. We can then plug in the expression for PB, which looks like this. We can do the trace trick again where we move this to the front. We get this. And now you can see we have this matrix V transpose B times its inverse. We'll assume that B is full column rank. So basically this cancels. This gives us identity matrix. And the trace of this R by R identity matrix is just R. Okay, so two things. The sum of, individually the alphas are between 0 and 1. Second, their sum is exactly equal to R. Okay, so finally we have this new optimization problem just in the alphas, which goes like this. Find these capital R alphas where all of them are between 0 and 1, and they sum up to R to maximize this. And I'm going to argue that this is something you guys all know how to do because it's something essentially you would do when you walk into a store and you want to buy some stuff and you have particular products you like and products you don't like, and you know how to spend your money. So it goes like this. So alpha j is going to represent how much you buy of the jth item. You're allowed to buy between 0 and 1 unit of the jth item for all the different items. But in total, you must buy R items. Okay, so between 0 and 1, so at most 1 item you can buy, and in total R items. And you want to maximize your total joy. So let's say when you buy 1 unit of the jth item, that gives you a reward of lambda j. So this is your total reward because alpha j is how much of that jth item you've bought, and now you're just summing across all the items. So you go into the store, you can buy at most 1 of each item. You have to buy R items in total, and you want to walk out with your favorite items. So, probably not too surprising. The thing you want to do is you want to buy 1 unit of your R favorite items. One and no more, no less than 1 unit of your R favorite items. Don't buy any units of any items you don't like. That's what you want to do. So to write it in terms of the alphas, because we had ordered our lambdas from large to small, it means that the first capital R alpha j's should be 1, and all the remaining alpha j's should be 0. So basically that's the solution to these to this problem stated in terms of the alphas. Any questions on that? Does that kind of make sense? So now that we know what we want out of the alphas, I'll try to convince you that the way to do that is just to set B equal to this VR matrix, equal to a matrix with columns V1 through VR. The reason is if you go back to the definition of PB, it used to be B transpose B inverse B transpose. Now we're just replacing B with VR. You get this. But VR has orthogonal columns, so VR transpose times VR is identity. So identity inverse, that whole thing goes away. You're left with this. And now remember that alpha J had this form. We plug in this matrix here, and you can see that because Vj, that is just the different, those are, when J is between 1 and R, those are the different columns of this. Those columns are all unit norm, they're all orthogonal. So essentially, this choice gives you these alphas that you want. So that's essentially the end of the proof. Boiled it down to the alphas, we figured out what alphas should be, then we figured out here is at least one way to get those alphas in terms of B, and we're done. Yeah, so a lot of linear algebra, but nothing you guys can't handle. All right, any questions on this? Okay, so we've proven Eckert-Young. Let's just summarize what PCA is doing then. So we have this centered data xi, where I goes from 1 through n. You compute this sample covariance matrix. You compute then the eigenvectors that correspond to the R largest eigenvalues. That gives you the B matrix, and now essentially you say, okay, the best approximation to xi, actually there shouldn't be a hat here. So xi, the best approximation to xi is this. And so here's our B matrix. And in order to make the zi hats, we just take those xi's and we multiply on the left by B transpose. Okay, so that's the PCA solution. These eigenvectors are called the principal components. And we know that the approximation projects X onto the subspace spanned by the R principal components. That's essentially what it's doing. Okay, so this idea just shows up all over the place. Like I said before, it's not a cutting edge idea, it's not a high performance idea, but it's very fundamental, and that's why I think it's a good thing to learn in an introductory course in machine learning. A lot of my grad students that take this course at some point, like always somewhere in their research, we come back to this. I'm like, remember those PCA slides? Go look at them again. That's how we prove this, or we already did this. So yeah, so it shows up all over the place. Okay, any last questions? All right, so we'll do maybe one more slide. So as was noted, when we do PCA, the rank of the approximation to R, this is a design parameter. This is something we need to choose. So how do we know when we have a good choice? So essentially what we're going to do is we're going to construct a metric called proportion of variance. And it's going to look like this. It's going to be 1 minus RSS divided by n times the trace of Q. So you might say, like, okay, why construct it this way? Well, it's very similar to R squared that we saw in linear regression. Of course, this R is not the same as the PCA R. This is just what we called R squared. In that case, it was 1 minus RSS over n sy squared. Well, remember, we don't have any targets now, so we don't have this sy squared. Instead, we replace that with the trace of Q. And essentially, you can see it works in a similar way. If the approximation is perfect, the RSS goes to 0, and you get proportion of variance equal to 1. And there's a similar thing if you essentially like use no coefficients. I believe this POV will shrink all the way to 0. If you do PCA with like a rank of 0, so that would be the worst case. You're essentially not you're not describing your data at all. So anyway, this is what we're going to use to choose R. We can make plots of this POV as a function of R, and we can see when this thing is sufficiently close to 1, we can feel pretty good about our PCA approximation. Okay, so let's take a closer look at, okay, what happens with all this. So, okay, n trace q, what is that? So n trace q, we know we can replace q with v lambda v transpose. We can move this to the left side inside the trace, then it will cancel this, so all we get left is n trace lambda, which is nothing, because lambda is diagonal, that's nothing more than n times the sum of our eigenvalues. And this is all our eigenvalues, 1 through d. What about RSS? So we previously derived that RSS is n trace PB perp Q, and then we also saw previously we can expand that this way. This thing we already computed above here, so that's this. And this last part, this is something that we also computed in a previous slide, gives us this. And so these sums look the same, except one of them contains all the eigenvalues, the other contains only the top R. So when you subtract them, now you get this sum where you start with R plus 1 and you go to the end. So now that we know both of those terms, we can put this in the numerator, put this in the denominator, and we can take this 1, and we can write the 1 in a fancy way. It helps us simplify. And in fact, effectively, we look here at the sum over everything minus the sum of the end coefficients. That just gives us the sum over the first R. And in the denominator, we just have the sum over all of them. Okay, so here you can see the largest you can make this would be 1, and that is when you take the rank of your approximation all the way to the size of the original data. So you're not doing any approximation at all. At that point, you get POV exactly equal to 1. And if you took all the R all the way to 0, so you're basically just approximating all your xi's with 0, then you get a POV of 0. So that's sort of like the worst case. Okay. And everything else is in between. So, so we will see for a particular data set, we'll make some plots of POV versus R, and we'll see that, yes, this thing increases. And when it's high enough, that's going to be a pretty good place to choose R. Okay, so I think that's a good place to stop for today. We'll talk next time about a little bit more details, how we compute it efficiently, and then we will we'll look at an example with a face data set, face images, and we'll compute these things called eigenfaces. So see you guys on Friday.